To welcome you. We have an interesting program tonight. I'd like to introduce Dr. Dan Ohnemus. Dr. Ohnemus joined us from the Bigelow Lab in Maine in 2018. He's a chemical oceanographer. He received his bachelor's degree in biology and chemistry from Williams College, and then a PhD in chemical oceanography from the MIT Woods Hole Joint Program. So without any further ado, Dr. Ohnemus, take it away.
Thanks, Mike. Yeah, some great introduction there. It's so good we got to hear part of it twice. So yeah, hopefully you guys can bear with me for any bad jokes. You'd think at this point in the semester I'd be used to lecturing or talking to small boxes on a screen, but I'm sort of not. So we'll sort of take it how it goes. So yeah, thanks again for the introduction. So yeah, as Mike mentioned, the topic here is a look at climate mitigation solutions, ideas for the century ahead. I chose this topic quite a while ago, and now that the talk's written and being presented, I sort of wish I could change it, right? I would like to put solutions in quotes, quotations, somewhat sarcastic quotation marks, or maybe change that word to strategies. So I'll try and clarify some of those points sort of as we go through here. So let's take a look at an outline of what we'll look at tonight. So climate mitigation solutions, ideas for the century ahead. I want to point out, first of all, that many of these specific strategies and solutions we'll be looking at are still in the idea stage, right? So many of these are nascent technologies or nascent ideas that are not necessarily too far beyond the theory-based point in the scientific literature and in the public discourse. A lot of these images, like you'll see here, so this image of marine cloud brightening technology, these are renderings, right? And in some cases, in most cases, these technologies don't exist. And so we're sort of talking about ideas here in some sense. But there's still some grounding in reality, which I've tried to create as a touchstone for these topics. So what's the outline for tonight? So I thought I'd sort of walk you through some of the motivations for looking at this topic, specifically the motivations for looking at strategies for reducing climate warming, and try to make some key points early on about why we're looking at these technologies at all. And I thought I'd sort of ground it, these sort of, in many cases, this is sort of a litany of things that are worrisome that keep climate scientists and oceanographers and scientists like myself up at night. And so I thought I'd shift gears after that and look at a few past success stories. So to ground our consideration of these ideas and the fact that even though they're still ideas and they're in many cases very risky and sort of frightening ideas in some cases, that there are past success stories for dealing with large climate or global scale problems. And so I thought they'd be nice touchstones to put in there. Then we'll look specifically at two technological ideas that are based on atmospheric albedo and reflecting sunlight back into space. We'll look at stratospheric aerosol injection, specifically the first one, and then we'll look at a technology that is proposed to take place in the lower atmosphere, in the troposphere, closer to ground level, called marine cloud brightening. So those are the two radiation-based methods we'll look at. And then near the end, I'll also bring up carbon trading markets, and carbon trading technologies that are designed to reduce the actual underlying cause of global warming by reducing greenhouse gases in the atmosphere itself. And so these are pretty different topics. What you might also notice is that this is a climate mitigation solutions or strategies talk, but there are so many different technologies and so many different ideas out there. Those of you who know me and my research personally know that I work on trace elements and specifically look at iron and other elements in the oceans. And one topic that's not on this list is like iron fertilization, which you might have heard of. And I also don't go too much into a lot of these negative emission technologies that carbon trading markets have inspired. So the different actual strategies for reducing greenhouse gases is not the specific topic here. And so, yeah, there's a lot left unsaid in this type of topic. So I really encourage you, if any of these ideas strike your fancy or frighten you, or you're interested in the consequences or things that are left unsaid by the talk, I encourage you to look these topics up. Many of these topics here are actually presented at a very accessible level for the public because the public discourse is an important part of their consideration. And then we'll end with some conclusions. Okay, So let's get started. So let's look about these motivations here. Why did I decide to make this topic on climate mitigation strategies? And part of it, like I said, is that it's sort of like a negative aspect here, which is that climate change is often a really depressing and multi-fanged topic. And so, as we know, and many of you who are friends of the Institute and have been to climate-related talks have seen this graph before. This is the concentration of CO2 in parts per million in the atmosphere for the last 800,000 years based on ice core records. And the sort of key point from this hockey stick graph, as it's often called, is this really large increase, this huge excursion from natural levels of the last 800,000 years above the natural background concentrations of CO2. So each of these sort of fluctuations here is associated with an ice age and an interglacial period of climate warming. And so these huge variations in natural intensity of greenhouse gases are greatly being overpowered by human activities since the Industrial Revolution. And so some of this is the underlying cause in a lot of ways of of climate warming, which will be the focus of this talk, and the strategies at mitigating it. But the other sort of context here is that in many ways, climate change is an ongoing experiment, right? We are adding these gases, in this case CO2, to the atmosphere. It's an ongoing experiment that in many cases has measurable effects, but also has really uncertain outcomes, things that sort of keep myself and others up at night, and probably you as well as members of the concerned public. Okay, so let's think about one of the first consequences of this emission of greenhouse gases to the atmosphere. And many of you have seen this in different forms over the years, but this is basically a compilation of data from historical meteorological sources, looking at the average concentration of the atmosphere over time since the 1800s, and with 1950 being the average here. And so what we'll see is that no big surprise to those of you who have been to a climate talk before, the planet is warming, and it's warming quite rapidly within the last couple of decades. This warming is uneven. It's especially concentrated in the Arctic and in over land masses in Europe and North America. And this process is accelerating quite quickly over the last couple of decades, right? With basically every couple of years, we have our warmest year on record due to this sort of increased emissions here. So this is sort of this is why it's slide 2. This is something that we always come back to as far as climate warming, is this persistent warming of the planet associated with greenhouse gases. So no big surprises there, but I think it's still worth seeing, right? Okay. So the other things that we're used to probably seeing as those who are concerned about climate are these sort of images of greenhouse gas emission and temperature warming. But we also think about, we often are confronted with these images of the pathos of the polar bears, right? So the polar bears in a warming Arctic, right? We see images like this all the time in the press when climate change is discussed, with heart-wrenching imagery of these in this case, these are polar bears, right? Vulnerable organisms. And this sort of adds to the depression of the topic. And so this is sort of one of the reasons we think about these things, but we can be a little bit more quantitative here, right? So those of you who came to Chris Marseille's talk, we can look at data of these things to show that it's not just sort of this pathos, these imagery, but also in real data, we see, in this case, the extent of daily Arctic sea ice for the last couple of decades grouped into different years. And we have the 1980 to 2010 average here in gray, and then progressive in 5-year bunchings from 2010 to, from 2005 through 2019, different years with the extent of sea ice basically slowly declining over time in the Arctic, with 2012 being the record minimum year when the ice reaches its minimum extent in September, right? So again, we've seen this before. The consequences of warming are things like this, like the Arctic sea ice decline. The other sort of motivation I often come to, images that I think about when I think about climate change are the melting of prominent glaciers worldwide, right? So these sea ice effect is also true of landlocked ice, which covers about 10% of Earth's surface. So in this case, we're looking at the decline in the Saskatchewan Glacier, which is a major outlet glacier in Alberta, Canada. And since images were first taken of this glacier in the 1920s through just about a decade ago, this glacier, like many others worldwide, has retreated by several kilometers and greatly thinned as a consequence of this warming, right? So these images are from the American Geophysical Union. So lots of sort of pathos images here. But what I thought I'd do is also think about some of the more direct motivations here for this type of mitigation strategies that we'll get into. And what I'm getting at here is that it's not just images of and data of like changing cryosphere or vulnerable ecosystems, but it also, there are key human effects that we should actually think about that are probably in many ways more important, right? So let's look at one of these maps here. So this is a map of the annual centers of biomass for 3 economically important species in the northeastern United States. And the colors of these species go from cool colors or faded colors in the 1960s through data from 2015 and bolder colors. And of course, the coloration here is pretty bad. American lobster in maroon and red hake in blue for some reason, and then black sea bass in green, naturally. But what we see is that some of these consequences of a warming environment and the shifting of ecosystems are actually shifts in important economic species. So over time, the landings and locations of these species centers of mass have moved northward as the climate warms, and these organisms basically try to stay in temperature regimes that can continue to support their ecosystems. And so this is starting to bring these effects away from these sort of emotional images and the things that actually sort of affect us as humans. And I often think of these as being the really key motivators, the things that actually probably should keep us up at night, or these types of shifts. Another consequence of a warming planet that we've seen probably in different ways, but is worth looking at again, are changes in the water cycle. So a warming atmosphere holds more water vapor, which changes when and where and how intense precipitation events occur. So these are data from the US EPA presented by the United States Union of Concerned Scientists, which has a lot of really interesting and great resources for looking at these topics if they start to fancy. So we're looking at here are predicted precipitation changes through 2090, so through the end of the century in 20-year groupings. And at the top, we sort of have our worst case scenario here. This is our RCP 8.5, or representative concentration pathway 8.5. It's often seen in the literature about climate change. This is sort of the worst case unmitigated business as usual plus extra emissions, where basically nothing is done to reduce greenhouse gases over the course of the over the course of the century. And what we see here, and then sort of RCP 4.5 down here below is more of an intermediate pathway. So as reports continue to come out, the 4.5 pathway, or somewhere between 4.5 and 8.5, are generally considered to be more increasingly likely as time goes on and as our sort of strategy shift. But either way, the takeaway from this image here is that there are going to be measurable changes in precipitation in the United States. So in both of these scenarios, the intensity and location of intense rainfall events and precipitation is going to change in the United States as the atmosphere warms. And of course, intense rainfall events and the flooding that follows them are likely to become more common as the precipitation intensity generally increases in the United States. So big shifts in the water cycle also associated with the warming, things that we should care about. Another one that now that I've moved from Maine to Georgia, I think about more frequently, especially now that the seasons are shifting again, is longer and more intense summers, right? So this is a map of from similar data set of the intensity of summer days, so days that are over 90 degrees Fahrenheit. And in both pathways here, both the worst case scenario, sort of in our intermediate scenario here, there are generally going to be an increase in the number of days or over the historical baseline from the end of the 1900s. And so these number of days are going to increase as the atmosphere warms. Not surprising, right? Warming atmosphere, more intense and earlier onsets of summers, right? So this shifting in the seasons and shifting of where water and heat are located on the planet are really important to us. The other thing that I think really drives these points home is the sort of combined effect here of climate and water intensity cycling. And we often see this parameterized in the case of agricultural yields. So this is one potential look at this combined effect of water cycle and temperature cycle shifts on the location and yield of agricultural crops. So in this case, we're looking at the sum of corn, wheat, and soybean crops at the end of the century. So at the end, approaching 2100 here. And these agricultural yields are generally expected because of this warming and changes in the water cycle to lead to large agricultural yield decreases in key states that we care about, where corn, wheat, and soybeans and cotton are being produced. So the Corn Belt and California's Central Valley over here are expected to see agricultural yield decreases. This will also shift some of these ecosystems to more the northerly climates. And so there's been quite a bit of a land grab for fertile land in the Dakotas in recent decades as part of this predicted shift. And of course, this is actually not something that I'm much of an expert about, but I think it's a really interesting consequence here. And so this sort of agricultural like combined effect here is, I think, really drives these motivations home, which is that this isn't just melting glaciers in somewhere like north of 60 degrees north. These are having effects close to home. And so when we think about mitigation strategies, we're starting to think about these human effects as being one of the reasons we might try to alleviate climate warming in general. And of course, I just made these points, so climate change is a depressing and multi-fanged topic, but it's these sort of human and societal impacts that are actually the things that mitigation strategies are most targeted at. And I sort of wanted to drive that point home that this is not necessarily pathos for the environment or pity for the environment for the environment's sake, but these strategies are about basically reducing these negative human and societal impacts and allowing us to have control over things like agricultural and geopolitical security, stabilizing these ecosystems and increasing the predictability of these ecosystems serves all of these human interests. It serves our economic security as a nation and also like as a species. And it also allows us, and this is sort of an interesting side point, consideration of mitigation strategies and these choices that we'll make about whether or not to implement these things are going to be part of a larger discussion about national self-directedness. So in other words, how individual nations will react and adopt these strategies as part of addressing an international problem, right? There's a big difference in scale in some cases between the size of global warming type problems and the actors or the regions and locations that might be making decisions to implement these strategies. And so there's some really interesting tensions here built into the system. So not necessarily about these images of polar bears starving, but about images of potentially about us starving in some sense. Okay, so like I said, that's a pretty negative, and despite my smile, a pretty emotional look at the system. So let's think about some past successes. And the two examples that I chose here, the first of which is acid rain. And so as a child of the early 80s, I sort of grew up during this debate. What is acid rain in general? Let me get too sidetracked. So acid rain is basically caused by the lower atmospheric release of sulfur dioxide, SO2, and oxides of nitrogen, NOx gases from the burning of fossil fuels, especially from coal power plants and vehicles. And so these releases generally happen at ground level or close to ground level. And what happens, right? So when these gases are released to the atmosphere, they basically form strong acids that cause damage to human infrastructure and ecosystems when they rain out or those air masses contact the land upwind, right? And so, like I said, as a child of the 80s, I remember being confronted with these types of images, right? So acidic destruction of human assets, especially like statues and limestone and marble buildings, right? You see these like famous or statues with their faces burned off. But we also think about the agricultural effects, right? So acid rain or acidity in rain or added acidity in rain leads to acidic reactions in soils, which leads to agricultural effects. So in this case, the death of large sections of forest in Europe that are downwind of industrial areas, and also potential reductions in viable cropland. And so acid rain was a big problem, and it scaled with our industrial processes. Those processes scaled. So actually, and like I said, this is a success story. We did something about it, right? So acid rain is a success story because through, at least in the United States, through the United States Clean Air Act revisions in 1990, sulfur dioxide gases and acid rain causing gases are now scrubbed. So in power plants, the flue gases are now basically scrubbed through wet reaction with reactive minerals to remove these gases before they're released. And this is part of an effort called cap and trade, right? You may have heard this before, but basically this is legislation that attaches costs to the reduce of the emission of industrial pollutants, in this case, sulfur dioxide gas, and then also sets goals for their reductions by reducing the cap of allowed in this particular trading system over time. I should also mention that these other gases that also have similar acid rain effects are converted to N2 gas in catalytic converters of your vehicles, right? So we attack this problem in several different ways, but the end result was what we see in this map here, which is that shortly after the enactment, and actually relatively rapid decline in these industrial gases in this process, the deposition of sulfur in areas upwind of coal burning power plants decreased very quickly to low levels. The problem hasn't completely gone away, right? These gases are still released to some extent by a lot of process, but it's a success story in that we actually decided to do something with this problem and largely were able to do that. I also brought this up because sulfur dioxide will come up again later on as one of the constituents in aerosols. Okay, let's think about one other success story. So the one that sort of hits close to home as a trace element chemist is the de-leading of gasoline. So the context here is that tetraethyl lead was a gasoline additive added as an anti-knock agent and an octane booster beginning in the 1920s in the United States. It wasn't without debate. It was known that adding lead to gasoline was a potential risk. Of course, the actual enactment and the adoption of leaded gasoline did occur. And as those of us who grew up in the 80s also know, lead is a highly neurotoxic poison, right? So it's especially toxic to developing children. And it's associated with poor educational performance and even in some sources, elevated crime rates. And so as the earlier legislation with acid rain was discussed, 1970s amendments to the Clean Act basically phased out the use of leaded gasoline, this tetraethyl lead additive. And so it's a success story. And in this case, this is actually some specific data. So this is the concentration or consumption of leaded gasoline in thousands of metric tons per year. We can see that the United States was the largest adopter and largest emitter of leaded gasoline, which is why this legislation in the United States was so important. But we see that basically beginning with similar types of cap and trade legislation for lead as enacted by the Clean Air Act resolutions in 1970, the concentration of this pollutant in the atmosphere dropped off really quickly over time. Well, actually, we're looking at the consumption here dropping off over time, followed quickly by similar strategies in Europe, in European emitters. And so, and this is a success story because not only were these was the additive, this toxic additive phased out, but it also led to very quick changes in the human environment and the natural environment. And so the EPA mandated trading market for lead credits, rapidly reduced its utilization in US motor fuels. It was followed very shortly afterwards by a ban of lead usage in paint and new pipes, although some of those processes are more persistent still today. But in general, like I said, the consequence here was a rapid decline in the blood level concentrations in the US population. So the green curve here is the average lead level in preschool children's blood, beginning in the 1940s through the banning of leaded gasoline in the early 70s. And we see that this banning of leaded gasoline also led to very rapid declines in the concentrations in human blood. This data, it's really hard to find a version of this data set that also doesn't include this correlation with violent crime reduction over that time, which is a sort of a different debate about whether this is a cause and effect here. But yes, the point here is that we decided to do something about leaded gasoline and actually managed to do it. The other point that I wanted to make is that human effects were also coincided with environmental effects. And so actually the same author, Ed Boyle from MIT, has almost made a career out of measuring lead in the oceans. And this is a series of data from Bermuda. So these are concentrations of lead in the ocean from the surface of the ocean down through the bottom of the ocean, so 4,500 meters at Bermuda. And of course, Bermuda is just off the east coast of the United States. It's downwind of industrial production. And so deposition of lead from leaded gasoline from aerosols was especially prominent in this location. So Ed's data set begins in the 1980s, so about 10 years after leaded gasoline was banned. And what we see is that the concentrations of lead in the upper ocean decreased quite rapidly over the next couple of decades. And Ed is actually still making these measurements today. And of course, like different industrial pollutants will behave in different ways, right? Lead is not an analog for carbon by any means, but What I am trying to get across here is that making these actions as the human emitters of these things will actually lead to downstream consequences. So we can do something about these problems if we choose to do it. Okay, so let's shift gears again and start thinking about some potential strategies. And so the two strategies that I'm going to talk about first are basically solar radiation management strategies. And I apologize in advance because discussions of climate mitigation and climate topics in general has a lot of acronyms. And so I tried to scale down the number of topics that I talked about and the abbreviations that I use. But I thought I'd show SRM, solar radiation management, as an actual acronym because it comes up so frequently when you look up this literature. The other term that comes up a lot is the term geoengineering. And for the purposes of this talk, we'll consider geoengineering to be these types of large-scale efforts, so specific efforts at reducing climate impacts through actual infrastructure efforts. And these efforts are things that have a global scale of effect and also global scale effect. So they affect the environment over global scales or really large regional scales, which means that not just the actors who are doing these potential operations need to care, everyone globally should consider these options. The other thing here, when we talk about solar radiation management, are some couple key terms here. So most of these two terms that we're gonna, these two strategies we're gonna look at are basically built around increasing the reflectivity of the planet or the albedo of the planet. And we'll look at two different strategies. One of them is based on stratosphere, addition of aerosols to the stratosphere. And another one is basically a troposphere addition here. And so this greatly simplified diagram here tries to get across the point that the stratospheric technique that we'll talk about first is basically occurring at a level in the atmosphere above where most weather and precipitation occurs. And the touchstone for this might be if you've ever taken a flight on an airplane, which is in my case, I haven't done that in a long time now, so I almost forget what it's like. Maybe someday I'll travel again. But the stratosphere, the lower stratosphere where airliners tend to cruise, they cruise at this level because it's above the level of storm events, right? And so the atmosphere is relatively quiescent up here and there's relatively little precipitation. The atmosphere is dry as well. And so not only is that one of the reasons airliners fly at this level, but it's also a good target for climate strategies because precipitation processes that will wash these additions out are generally not going to occur at these levels. Whereas additions to the atmosphere, alterations to the atmosphere and the troposphere where weather does occur are generally going to be shorter effects. And so like I said, the point here is that these two strategies we'll look at first are basically designed around increasing the reflectivity of the planet to reflect incoming solar radiation to prevent the planet from warming. And this isn't a talk about the heat budget of the Earth or all these different fluxes and arrows in and why the atmosphere is actually warming. But the general point I want to get across is albedo reflection, increasing the reflectivity of the planet is going to help cool the planet. And we'll actually see that this does occur through natural processes. The other key thing about these solar radiation management strategies is that they don't actually address greenhouse gases, right? We're talking about increasing the reflectivity of the planet, not about actually decreasing the concentrations of greenhouse gases. And so the third, of these things that I'll talk about, carbon markets here and greenhouse gas removal, this actually does do this. Right? So these removing carbon dioxide from the atmosphere or reducing greenhouse gases concentration in the atmosphere through negative emissions actually does remove the warming pollutants themselves. And so two different sides of the same coin here. Another thing that I wanted to mention too is that only these sort of carbon reduction or greenhouse gas reduction technologies will actually address some of the other consequences of climate change, which include ocean acidification, right? So the acidification of the oceans through the addition of CO2 to the atmosphere is only going to be alleviated if you actually take that CO2 out, not if you just cool the planet. And so there's quite a few different tensions here on these different strategies. Okay, so let's look at the first here. The first one that we're looking at is stratospheric aerosol injection, or SAI. And the basic concept here, as I said before, is to release reflective aerosols or aerosol precursors like sulfur dioxide gas into the stratosphere to increase the reflectivity of the upper atmosphere. And as I mentioned in the previous slide, the release of in SAI processes, the release of these aerosols into the stratosphere is generally above the level of precipitation, which allows the persistence of these additions or any such additions to the atmosphere to stick around for longer periods of time. So it increases the residence time of these particles in the stratosphere. And this technology is generally based on the cooling that's associated with natural events. And so the sort of natural touchstone for this is volcanic emission events, which sort of naturally, because volcanic events are natural events, volcanic events naturally release these types of gases into the stratosphere during large eruptive events. And so the picture here is of the eruption of Mount Pinatubo in 1991, showing pretty clear injection of large amounts of sulfur dioxide and other volcanic gases into the stratosphere. And so this is sort of actually a surprisingly close view of this. But we can also see the effects of this type of stratospheric aerosol injection in space, from space. And so let's take a look at that. So these images here are of aerosol optical depth, or basically the reflectivity of the atmosphere before and several years after the event of the eruption of Mount Pinatubo here. And so the scale is shown here on the bottom. It's not really super applicable. You have to worry about the actual details here. But by this particular metric and by many atmospheric metrics, the reflectivity of the atmosphere increases very rapidly after you inject sulfate aerosols into the stratosphere. These aerosols disperse as the atmosphere mixes over the next couple of months. And so we see this basically tropical eruption from the Philippines spreading out over the course of the globe over the next couple of months, and then dispersing to higher and higher latitudes over the next couple of months. And then this reflectivity signal is still present in the atmosphere up to a year and a half later. So this is 1993 and 1994. So now we're talking 2 or 3 years later. There are still measurable amounts of these aerosols present in the atmosphere. And so this natural release of reflective aerosols or aerosol precursors into the atmosphere should cause cooling, and it does, right? So this happened in modern times. We actually have the data for it. So this is an image from NCAR and DOE of the global average surface temperature, and they've marked the key volcanic eruptions of the last century and a half or so, with Pinatubo being right here. And we can see that these large eruption events basically cause noticeable decreases in the temperature of the planet for several years, up to a decade afterwards. And so this temperature decrease as a result of these stratospheric aerosol release events is a noticeable thing, which means that in a lot of ways, if we were to adopt this strategy or scale up sulfate addition technology to the stratosphere as humans, that there's pretty good evidence that it would work, right? So as a process, it's fairly clear that this actually would probably be able to drive the effects that we want them to. But of course, that's not the only thing, like whether or not it worked, right? So SAI, stratospheric aerosol injection, has huge potential global implications, right? We're talking about cooling the planet over large areas through huge scaled up, if they were to be scaled up operations, right? Currently, there are no really good international regulatory systems in place to describe how we could make these types of decisions as a human race, right? There are also lots of uncertainties about it, right? And some of the things I've mentioned here are questions of location. So some of the things I wanted to get across are that when you read this literature is that release into higher latitude environments, for instance, the Arctic, the part of the planet that was warming the fastest in that early slide, showing the warming effects. So releasing these types of aerosols into the stratosphere of the Arctic would have different consequences than if they were released in the tropics, like Mount Pinatubo's eruption. And one of the things that's discussed often is that release into higher latitudes in the Arctic would in some ways be easier because the stratosphere is located at a lower level, so 8 or 9 kilometers versus 16 kilometers, meaning that it would be physically easier to get these aerosols into the atmosphere at higher latitudes. One of the other interesting consequences due to atmospheric dynamics is that the residence times of these particles in higher latitudes would be shorter. And so these types of geoengineering efforts, if they were to be enacted, one of the major concerns is how long these effects would last. And so one of the potential benefits, if you want to call it that, of doing it in higher latitudes is that the residence times of these aerosols would be more on the order of months rather than for multiple years. And so some folks who will advocate for this potential strategy will argue that you could do more seasonally based injections, where you basically release aerosols, say in the spring before the Arctic starts to warm, and then basically have your strongest effect during the summer months, and then those aerosols would be dispersed or washed out of the atmosphere over before the next season. And so these types of discussions about the potential feasibility impacts are just one of many aspects that folks consider when they debate these topics. There are also other really important questions about methodology. So specifically, which aerosol precursors would be released, whether or not, and this is what this image tries to get across here, how this would be done, right? So whether these releases would be done through military aircraft or through structures that don't exist yet. So stratospheric towers that would have to be designed and built to actually pump these gases up into the atmosphere. Some of the actually more feasible aspects of SAI are the idea of using artillery shells to deliver these types of gases. Not necessarily sulfur dioxide, but things like aluminum oxides that might have similar effects. So basically shooting explosives up into the atmosphere to deliver them with unmanned approaches. There are discussions and images in the literature of using balloons or tethered balloons to basically loft these chemicals up the atmosphere in a more controlled way. Whether they were tethered or untethered is part of debate. So these types of strategies, sort of as our first look here, are basically, they're still nascent, right? These are still being hotly debated. There's lots of papers about the potential costs of different types of strategies. Trying to scale up something that you do as a proof of concept to something that would actually have an effect on global climate is a really interesting and challenging exercise. And so that's sort of the state of this current technology, at least as I saw it in my review of the literature. Okay, so let's shift gears a little bit. So we talked a bunch about stratospheric aerosol modification. We can go a little bit closer to home, to the surface of the planet. So this topic is marine cloud brightening. So the idea with this strategy is to basically release fine aerosol forming particles, generally sea salt, over the oceans into naturally cloud forming regions that currently lack these types of aerosols. And so the idea here, like with stratospheric aerosol release, is to increase the reflectivity of the atmosphere. But in this case, we're forming or enhancing the reflectivity of near surface clouds in the troposphere. And like I said before, for the stratospheric approach, this actually has a natural analog as well, or maybe not perfectly natural, but we know that this process already occurs. We can see it in ship tracks, right? So this image here is of ship tracks off the Pacific Northwest from NASA imagery. So this is the coast of Washington, Oregon, and California here. And these lines here are basically ship tracks of the smokestacks of ships releasing sulfate and other aerosols into the atmosphere right near the marine boundary layer. And this smoke basically goes up in the atmosphere and forms clouds in these regions that currently lack the nuclei to form these clouds. And so similar to like an atmospheric or the stratospheric effect, we're now talking about enhancing clouds closer to surface. There's just like the stratospheric aerosol injection possibility. There's lots of questions here about its feasibility. One of the observations in the literature is that bright marine clouds, the type that would actually have an effect on climate, are only especially prominent in certain parts of the world, right? So we saw here in the Eastern Pacific, marine clouds and ship tracks are also especially prominent in the South Atlantic, the Eastern South Atlantic. And so this process wouldn't necessarily work everywhere. And so there's lots of debates about where it could be actually have an effect. The other thing that I wanted to mention when it comes to marine cloud brightening is the natural side of the equation here. And so marine cloud albedo, the reflectivity of marine clouds, is a subject of some natural research as well. And they center around this compound dimethyl sulfide, DMS, which is a sulfur-rich compound that's produced or from a breakdown product of DMSP. So DMSP, the parent molecule, is produced by a lot of marine organisms to help balance as an osmolyte, to help balance out their internal chemistry, basically. And so lots of organisms produce this DMSP precursor. And when these organisms die, they release DMSP to the environment. It's an energy source and an interesting biochemical molecule to lots of marine bacteria that break DMSP down into DMS. And then the ocean and atmosphere are in constant exchange. And so this volatile species of DMS is released to the atmosphere, broken down into sulfur dioxide, our precursor gas, our aerosol precursor gas here. And there's lots of interesting research that's hotly debated about whether this natural DMS cycle actually affects the albedo of clouds over different marine ecosystems. And so as this figure tries to show here, the release of DMS and eventually sulfur dioxide to the atmosphere can affect cloud albedo in the same way we saw these ship tracks affecting cloud albedo. This is a hot topic of debate, partly because it was like, wow, like organisms in the upper ocean might actually control the clouds above them if this process actually occurs. And so it's currently the subject of a lot of intense debate, not only whether or not this process occurs to the extent that it might, but also whether the intensity of marine cloud models are sufficient to actually have this be an important effect. So whether or not it occurs and also the intensity of it are hotly debated. It's also worth mentioning that albedo cloud-based effects in general are one of the more uncertain aspects of climate models. And marine clouds specifically can have radiative climate forcings from anywhere from negligible to very strong, depending on how they're parameterized in models. And so those aspects of albedo are also hotly up for debate. Another thing that's interesting about these sort of near surface phenomena is that they're slightly more approachable. And so in some cases, in this case, these are images from the Marine Cloud Brightening Project, which is based at the University of Washington. And some of these organizations have actually received funding with philanthropic help to actually start building test beds to see whether these types of processes would actually be feasible. And so in this case, we're looking at their test platform, Cloudia, which is a great pun, which is basically a proof of concept built onto a pontoon here. And the idea here is that you have these types of towers that can inject your sea salt aerosol into the atmosphere. And of course, as those of you who work with seawater, my colleagues will know, working with seawater is a really caustic substance and actually very difficult. And so a lot of these sort of mechanical designs of these types of ships have actually failed. So the actual mechanism of aerosolizing sea spray is very challenging and something that these folks have not been able to do successfully on the scale that would allow it to become a feasible technology. There's also lots of questions about how these ships would be designed, whether they would be manned or unmanned. But I should mention too that one of the potential perks or benefits of these nearer surface phenomena is that if we wanted to stop it or turn these technologies off, we could do that, right? You call the boats back in, and because these aerosols are being released to the troposphere, they're going to precipitate out in very, very short order, and the effects will easily be gone. And so there's lots of questions about responsiveness and the temporal variability that are interesting. The other thing that's sort of cool about marine cloud brightening as a concept is that it's thought it could be regulated under current UN laws, because these ships would basically be out in the open ocean in most cases. The UN conventions or the laws of the sea would apply. And so if these technologies were too disruptive or causing unnecessary harm, it's thought that we could actually regulate them without having to come up with entirely new ways of regulating it. So I think that's an interesting side point. Okay, so let's shift gears to the final point here, which were carbon markets. And so now we're shifting away from aerosol and reflectivity-based ways of cooling the planet to thinking about how to get at the root causes, so the greenhouse gases themselves. And I thought I'd give a quick overview of where these carbon markets and carbon pricing stand. So of course, the idea here is to attach a cost to the release of greenhouse gases. There are two main strategies with carbon markets. The first is ETS, or emissions trading systems, which is sort of our so-called cap and trade that we saw with sulfur dioxide. The other option here is a carbon tax, which is basically an uncapped system. So the emissions trading system actually has a cap that the regulatory body sets, and may even set the price of that. And a carbon tax is an uncapped system with an open cap and either a flat or a floating cost on the emissions themselves. And so there's quite a few different ways of parameterizing this economic space. But the benefits of these sort of carbon technologies or greenhouse gas-based technologies in general is it actually does directly address the greenhouse gases themselves, right? We're actually reducing or removing greenhouse gases from the atmosphere, whereas these aerosol or reflection-based methods are actually just cooling the planet. And that has some interesting consequences we'll see in the conclusions. The other thing that's great about greenhouse gas reduction technologies, they actually will address some of these other consequences of climate change that include ocean acidification. So the current status of this particular system is quite variable, right? A lot of these carbon markets, mixtures of ETS and carbon taxes have been implemented in different parts of the world. The ones that have received a lot of attention worldwide are the markets in Australia, New Zealand, and the European markets. Some of the European markets were begun at individual nation levels and are now starting to be linked. The markets are now linked between Switzerland and the EU and the UK and the EU. And so there's some really interesting debates that are happening public policy wise and internationally due to the quite variable nature of these particular markets. One of the other things that's usually noticeable when we look at these types of figures is that the United States is generally not participating in carbon trading at the national level, although we are starting to see increasing numbers of US states that are voluntarily participating in carbon markets and beginning these types of experiments. The other thing that I noted in looking at this literature, and I highly recommend you look at this, this article or this research publication called State and Trend of Carbon Pricing 2020, published by the World Bank, where this figure is from. It goes into great detail about what these different markets are and some of the public debate that actually occurred with them. One thing that I did love from these executive summaries is that these current markets only cover around 22% of global greenhouse gas emissions, right? So we're still talking not the lion's share of greenhouse gases being emitted. The other thing is that some of the newest markets, the biggest like innovations in the carbon trading space are actually happening in the Americas. So 2020, pre-pandemic, actually saw the emergence of pilot programs in Mexico and New Brunswick, Canada, which are the first large-scale projects in the Americas. Currently, the thinking on carbon markets in general is that the current prices are too low to meet international agreements like the Paris Climate Accord, the Paris agreements, to actually like have significant long-term effects. But it's also worth noting that many of these markets are new and evolving. So the markets themselves and the prices that are associated with the carbon being removed are constantly evolving. Another thing that I think is cool when we think about carbon markets is that actually that a significant number of companies nowadays are actually pricing carbon within their supply chains. And you probably notice this like at the grocery store and also if you work in industry. So my sister works in industry, which is financial industry, not even related to climate at all. And her company, like many others, is starting to consider going carbon neutral because they have customers in parts of the world that actually do care about these types of ethical decisions. So a lot of companies, even ones that are not based in these types of markets, are starting to make decisions based around pricing of carbon, which I think is an interesting short circuit in the system. Another thing that's cool is that a large number of these carbon markets, around 42% of the market shares overall, involves forestry and forest-based initiatives for removing or carbon from the atmosphere. And so one of the weird considerations about carbon markets is that in some cases, the main sinks that are currently being considered are spatially limited, right? There's only so much room to regrow forests. And so a lot of debate is around developing new technologies that don't necessarily have land-based caps on where the carbon can go. And so this is sort of the final point here, which is that the many possible technologies that will result from carbon market pricing forcing are currently under development and are being developed by lots of different actors. So, okay, so let's jump to the conclusions here. So as we saw, there's a wide variety of potential strategies to mitigate the challenges of a warming planet. The ones that we looked at are basically fall under the umbrella of solar radiation management. So we looked at stratospheric aerosol injection and marine cloud brightening. These are the two best research methods and the ones that are thought to be the most cost accessible and the most feasible as well. But like we said, these geoengineering strategies have huge risks and uncertainties associated with them. That makes funding them and having public discussions about them very challenging and difficult, which are not necessarily bad things, but because of their contention and risks, these are hot topics in a lot of ways. One of the things that I didn't mention in the talk and I wanted to show in the conclusions here are these risks called sudden termination risks. And what we're seeing here is a sort of schematic of time on the x-axis here and temperature change on the y. And in this particular scenario here, we have high emissions that are basically increasing over time under like a business as usual strategy. And the emissions of like a stratospheric aerosol injection to remove or to remove the effect of these gases and reach a temperature target would have to increase over time, right? And so if you continue to burn fossil fuels and you use these types of alternative strategies for cooling the planet, there's a huge risk that if these technologies turn off or are terminated, that you'll see a large increase back to really high untargeted temperatures. And so a lot of the discussion is actually based around using these types of methods as one potential complement to more complex strategies. So combinations of cutting emissions, emissions removal, negative emission technologies to remove CO2 from the atmosphere, and things like sulfur aerosol or stratospheric aerosol injection and marine cloud brightening and other technologies to sort of fill in the gaps over time where they could be scaled up and scaled down. And so this is, like I said, the topic of very recent and hot topic debates in high profile literature. And I strongly encourage you to look at these papers, because many of them, like I said, are written at a level that is understandable for those who are scientists and those who are not. And then also these sort of carbon market technologies that I went into in the end here. The key takeaway is that what I think is really interesting about carbon market technologies is the potential for them to short circuit these regulatory concerns, right? So market pressures will operate across international boundaries if companies start following these rules voluntarily. And so these types of carbon-based or carbon market technologies may incentivize slower moving actors to participate over time if the markets are developed in the right way. And another key takeaway too is that no single technology or strategic approach is believed to be able to solve climate problems on its own, which is one of the reasons that we're having these discussions at all in the literature is due to the fact that there are considerations, and we should be considering lots of options to address these complex problems. Okay, so feel free to type your questions into the YouTube chat, like I've mentioned here. If you have a longer point or wanted to follow up, feel free to send me an email. My email is just dan@uga.edu. And I'd happily take comments offline and try to get back to you in the long run if that's the approach you take. So thanks.
And thank you, Dr. Ohnemus. Great job. So I am Dr. Cliff Buck. I will be moderating the question and answer portion of tonight's activities. And so please do drop those questions in the YouTube chat. We've had a couple already. I've also got a few that I want to pick his brain about. So
maybe you can answer some of them.
No. This is your night. So we had one question come in through YouTube early on. This is pertaining to our discussion of acid rain and the Clean Air Act. And it's actually a great question. So when you refer to the chemical scrubbers, in the smokestacks, what without perhaps getting into the details of the chemistry, but what happens to those chemicals once they're scrubbed? I mean, presumably that's an exhaustive process, right?
Yeah, that's an interesting point. And actually, I will freely admit that it is not something that I know too much about. I do understand that, in some cases, this is, so let's think about it, right? So these reactive gases are basically generally reacted with things like limestones and easily ground up minerals that are going to react with these sort of acidic sources to form compounds that basically are non-toxic. And so I don't know for sure exactly where these gases are deposited in the long run. It would be really interesting to look up, and I'd love to follow up on it. My guess is that the relatively simple chemistry of some of these gases, and I'm sure there are plenty of reasons that it's actually quite toxic as well, but is that I'm guessing that there would be a lot of industrial processes designed around making and detoxifying this effluent so that it could be either put away like mine tailings or something like that into a system that can be monitored over time. The interesting comparison too that I don't know the answer to, but I will pose the question, is the scale of these emissions compared to other types of mining related processes, right? So the amount of sulfur gases that are released by flue gases very well might pale in comparison to, say, the amount of mine tailings that are being produced by potentially even more toxic processes, getting at things like phosphate and other minerals. So my guess is that because these are land-based technologies, that there are going to be land-based solutions around if these effluents are toxic, then keeping them in secure places. But who knows? I actually don't know the answer to that question. So.
Great. I'm going to ask this next question because I had the same question. Mr. Bruce Walker wonders, so what goes up must come down. If you're injecting all this sulfur dioxide into the stratosphere, I'm sure it has a residence time of some period, but eventually that's going to re-enter the troposphere. What then?
Mm-hmm. Yeah, exactly, right. And that's critically one of the things that the key questions that folks have when they think about these technologies. And based on my understanding of the atmosphere, you're right. Like what goes up must come down, and these same processes that are basically occurring with acid rain are going to occur in over larger scales if these aerosols are injected to higher altitudes. One of the potential ameliorating effects to the fact that eventually that sulfur will come down as strong acid in some kind of rain is that dilution is the solution, right? So you're diluting these aerosols out over significantly larger areas. And so I'm not trying to defend this technology at all, right? I think that these are actually extremely valid reasons that we should probably not go down this road. But is that one could argue that dilution of the atmosphere will actually distribute the acidic cost of these vapors over larger areas to the point where they might be inconsequential. But that is also very dependent on the scale of the process, right? So whether you're trying to actually reduce the forcing of all greenhouse gases currently in the atmosphere, or just trying to reduce it over a smaller area. If you were to, the other thing that I mentioned in the talk was the locations, right? So the location matters. If you started dispersing aerosols to the stratosphere of the tropics, you're going to have a very different fallout pattern than if you release these aerosols in the Arctic. And so, those questions about like where and how and who bears the cost associated with these releases is a huge aspect, right? Maybe I didn't say it explicitly, but like we should care if Russia starts injecting aerosols into the Arctic because they're going to land on Canada and the United States eventually, right? So yeah, it's a big part of that problem. It's one of the reasons we should probably be thankful that this is still a nascent technology and a theory.
I'm going to use my bully pulpit and follow up on one thing there. So, given the difference in kind of annual solar insolation at the equator versus at 60 degrees north, for example, I mean, in your research, did you come across estimates of the relative effectiveness? I mean, you went through reasons of why you might, do this SII process in the Arctic, but given that there's so much less actual solar energy reaching the high latitudes, I mean, what's the trade-off there?
Yeah, and I think you started to mention it, right? Which is that there is a trade-off there. The specifics about Arctic release versus tropical release, I'm not super versed on. But my take on it is that the seasonality of the system is an important aspect. And so I did try to mention that basically by targeting the release in a place like a highly affected region like the Arctic, you might make the argument that you could release aerosols over a shorter period of the year. So basically limiting the time that you're releasing it. And also that you could potentially get away with, because you're dealing with a smaller regional effect, releasing smaller amounts than if you wanted to have a similar effect over in the tropics, right? And so this ultimately gets to the question of what the goal of the technology would be, right? Is the goal of technology to reduce the rapid warming that's happening in the Arctic, or is the goal to reduce the temperature of the planet as a whole, right? And so you'd have to strategize about where you were doing these releases in order to answer that question. Does that get at what you were trying to say there?
Yeah, no, that's great. I mean, I thought, well done. So to follow on, I mean, we're kind of on the same topic here, but Charlie asked a question regarding the volcanic emissions, and you very clearly showed the change in temperature, which I think which is kind of intuitive. But she followed on to that, because she's in our lab group, and wonders what happens when volcanic emissions, do they have any influence on like phytoplankton blooms and surface ocean chemistry?
Oh yeah. Right, and you're right. This particular talk is a pretty broad brush about what these releases are involved, right? And also I should mention too that the composition of volcanic gases varies, right? Every eruption is very different, right? So the volcanic gases themselves, the ones that are driving these cooling, are more complex than just sulfur dioxide and H2S. There's also like actual ash and different types of minerals based on the location of the volcano and its sort of geology. And so, yeah, I think when we start thinking about these downstream effects that are not just atmospheric based, but are like regional phytoplankton bases, then yes, right. There are some cases like studies in regions that have been downwind of volcanic eruptions in Alaska and Iceland. We've seen or expected to see effects of the deposition of this material into the oceans. And oftentimes at least my understanding of literature is that those effects are not necessarily as intense or occur on the same timeframes that we might have expected them to. And so, we're talking more oceanography than climate warming, but the fallout of these different types of systems is pretty complicated and not one that we have a lot of experience with. And so, I think it's pretty hard to like plan on going out on a big research cruise and know that there's going to be a volcano that occurs, right? And so the periodicity and the actual challenges of doing this type of sampling is a pretty big consideration in our understanding of it, or lack of understanding of it.
Well, perhaps Dr. Marseille tomorrow in our lab group meeting can expand on some of this, as he's written on this.
Yeah, we have some lab group members that have been lucky enough to be in these scenarios before, right?
Yes. There's a couple more questions. So do you think that the geoengineering would be counterproductive, perhaps, to international efforts to shift away from fossil fuel burning?
Oh, meaning because these efforts would allow cooling to be disconnected from the source of greenhouse gases, that it would actually potentially encourage additional greenhouse gas usage, if I'm hearing the question correctly. And my sense is
right.
Yes, right? That is a very valid and actively discussed aspect of it, right? That final slide that I'll go back to here, it basically is making this point in a graphical form that if these technologies were, say, super cheap or very feasible with low risk, so we found out through experimentation that was the case, then we'd feel free to keep burning fossil fuels and keep emitting these things and making really slow or negligible changes to the emissions process. And so perhaps partially because of these risks, we might actually be more likely to take action on all fronts. And so maybe what you could actually see the riskiness of these potential scenarios as being like, well, we really don't have to pull the trigger on SAI and marine cloud brightening. So let's get our act together and actually reduce the greenhouse gases, right? Maybe that's one potential route for this discussion to go down. I will say too that we have had more active debates and actually ground level experimentation based efforts on ocean iron fertilization. And the discourse that surrounded that, the risks involved in that particular technology were pretty pointed, right? The scientific community came out relatively rapidly after certain actors started doing these types of experiments in the ocean for money, for corporate reasons. The scientific community came down pretty quickly on highlighting these risks. And I think if any of these technologies actually started to see use or active use, we would have pretty sharp debates about the actual risks associated. So yeah, I think as one potential tool, it clearly only fits the bill in that sense. It's very risky.
Right. I think there's another question about to come in, but before that happens, I just want to remind all Mars 1011E students who might still be here to submit their one-page notes and summaries of this to me for their extra credit.
My email does not apply.
Right. I did have one other question to ask, and again, it's a little bit more of a political international relations question than science, but because all of these things, as you kind of alluded to several times, are going to require very high level, large scale international cooperation that frankly would probably put the Paris Agreement to shame in terms of actual binding and action items and what have you.
Mm-hmm.
But I think that'll probably, that's going to cause a lot of tension among nations. Do you have a sense in your research for which nations are essentially the most responsible for kind of the CO2 emissions over the course of the industrial age, say like from 1750? There's a lot of finger pointing, and so do you have a sense for kind of if we were, how do we account for that?
Yeah, and so there's a lot to unpack there, right? And this comes up a lot in this conversation, like specifically the United States, right? We saw with the leaded gasoline, with the United States being the leading emitter of leaded gasoline over the course of the history of that toxic pollutant. My sense on it, having sort of been immersed in this literature tangentially for a long time, is that the EU as a unit, the United States and China, and growing capacity India, are largely considered to be the largest emitters, right? The most industrialized countries, the ones that industrialized the earliest, are the ones that have emitted the most greenhouse gases over their histories to get to the developed status that they have nowadays. And also, there's a big disconnect there between who is feeling the effects of these gases and those who should be doing something about it, right? There's lots of different roads that we can go down when we start pointing fingers about who emitted them and who should be doing something about it, for sure. For the purposes of this talk and the technologies, these sort of technological solutions around it, one of the interesting points that I wanted to kick back at you is the use of the word require in order to, like, say, when you said that any type of effort to use these types of technologies would require large-scale international cooperation. And one of the reasons I think these technologies are worth thinking about is that that's not necessarily true, meaning that if Russia decided tomorrow to start building stratospheric aerosol towers and developing them and releasing aerosols to the atmosphere, we don't have a great regulatory framework for like pointing fingers, right? Like, I guess we could declare a war on countries that were doing things we didn't want. But in a lot of ways, these technologies are feasible enough that they actually could be enacted by certain actors if they wanted to. And so the requirement for an actual regulatory system is not necessarily true, despite the fact that there will be like major consequences for everyone involved. And so, yeah, I think that's another interesting aspect for why we look at these topics is that, wow, like these are potentially very risky things that we haven't considered in our current framework. And so, yeah, when we start talking about who should be developing these technologies, who should be paying for them. The other thing I want to mention too that I didn't include when I originally like framed this talk were space mirrors, right? So we often, the really high level atmosphere process for dealing with incoming radiation is actually to put mirrors or some kind of reflective substances or engineering solutions in space to reflect incoming radiation. And I didn't know this, but maybe you did in exposing my my lack of knowledge on it, but Russia actually developed space mirrors with the opposite idea. And so in the 1990s on Space Station Mir, they released like about a 20-meter satellite, reflective satellite, that actually the point of it was to focus incoming radiation on regions that didn't receive it. It was a test experiment. And the size of the reflector they had in space, the mirror, was basically about a 5-kilometer based path on the Earth. So a 20-meter reflector focusing onto a 5-kilometer wide path. And so the focus brightness was like about the power of a full moon. But it turns out they actually did this experiment in space and were successful at it. So for the day or so that it was in space, it was noticeable from the ground in the EU and Russia, where they chose to focus it. And so, you know, it's potentially feasible, right? There are test cases that show that like actually we could be doing these technologies and there might actually be regulations in place. We have to build them around the emergence of the technologies.
There's some good points, and yeah, you're right. I had not considered the rogue environmental state. So
right. I mean, this came up with
that.
ocean iron fertilization.
That's right. So I think we are. Let me just jump over real quick to make sure that I'm not missing anything. I believe we've kind of reached the end of our program. I will turn the floor back over to you to advertise for the next talk and close us out.
Great. Sounds good. I don't know what happened to it. I had a slide on the upcoming talks. Oh, here it is. Great. I don't know if Mike wanted to unmute here, but and if not, then I'll start talking. But yeah, we welcome you to the next program in about a month by Dr. Adam Greer. A bit of a focus shift here to the secret life of ocean critters, and the rest of the schedule here for the Evening at Skidaway series is not only present in this slide, but also in an updating fashion on the website. So please take some time to subscribe to the Skidaway YouTube channel and bookmark our homepage to follow up with future events. And like I said, I really would love to hear from folks who wanted to write longer feedback or had questions by email. So feel free to email me as well. I look forward to hearing from you all.